Hola a todos, buenas tardes. Quiero daros la bienvenida a este webinar que hemos hecho en colaboración con Ted Pella. Estamos conectados con California, ahora mismo son alrededor de las 9 de la mañana. Quiero agradecer la participación tanto de los interesados en este webinar como de Courtney Ozzello y Blain Jones. Ambos son expertos en producto en el área de Life Science. Iesmat somos los distribuidores oficiales de Ted Pella tanto en España como en Portugal. Ted Pella es una empresa que se fundó en 1968 y desde entonces es una empresa líder en productos de consumibles para microscopía electrónica, anatomía patológica, histología y demás. Tiene más de 12.000 referencias. Cubre todas las necesidades que puede tener cualquier laboratorio. Este webinar va a tratar sobre preparativa de tejidos biológicos en resinas de baja densidad y también vamos a profundizar en tecnología de microondas para el proceso de los tejidos con un equipo que se llama BioWave. Quiero agradecer también los interesados que se conectan desde Portugal. Welcome for connecting from Portugal. And please, Courtney and Blain, please go ahead when you're ready. Courtney, do you hear me?
Yes, I apologize. I had muted myself.
Okay, no problem.
We should be
Well, go
better
ahead.
now. So I'm going to give you an overview of how to do your infiltration with Spurr's resin, which is a low viscosity resin for electron microscopy. So your first step is just gathering everything that you'll need. You don't want to be running through the lab to get stuff when you're in the middle of an infiltration. I've got a list of everything that you'll have here, which is our resin kit, which contains our ERL 4221, our DER 736, our NSA, and our activator DMAE. We also will have a fixed sample that's going to be in the solvent at this stage, an embedding mold for the final stage of embedding. I like to have all of my pipettes labeled with each ingredient to avoid contamination. And then you'll want to have some final containers to mix your resin in. If you're going to keep this for storage, I like to have a conical with a lid. If you're going to use it all in one day, a tri-pour beaker works well. And then you'll have something to stir the resin. We use a wooden dowel in the lab, as well as something to manipulate your sample into your mold. You'll want to set up near a fume hood or have the whole setup in a fume hood because the DMAE you do not want to breathe in. So your first step is going to be mixing your 100% resin to use through the infiltration. So we'll go ahead and take our labeled pipettes. ERL will be our first step, DER, followed by NSA, and then last we'll have our activator DMAE. You'll also have your solvent, a 100% resin, and a 1-to-1 solvent resin mix pipette. And the following amounts in the presentation are all based on a full batch that was provided, which is based on a 1 millimeter cube sample. So your first step is to tear your scale and weigh out 4.1 grams of your epoxide resin. And then to that, you'll add your DER 736, 1.43 grams, followed by your NSA, 5.9 grams. And then in the hood, you'll add your activator, and this must be added last, and you'll mix it into the 100% resin in the hood. And you want to continue to mix this until you get a homogeneous mixture. As you can see on the right here, this is what you're going to see as you first start mixing it. You have different viscosities, and so you'll get these wave patterns. Once you have a homogeneous mixture, these will disappear. And then you know you have it thoroughly mixed. You want to mix very gently to avoid air bubbles. If you do see any air bubbles in your final resin, you can go ahead and place it in a desiccator under gentle vacuum, and that'll help remove those. So now that you have 100% resin, we need to make a middle stage for your sample to go into. You don't want to go from 100% solvent into 100% resin. It won't infiltrate as well. So you like to have a middle stage, and we could do a 50% of each solution. So we'll make a 1-to-1 solvent and resin solution. We don't want to take all of our 100% resin that we've made. We'll want to leave some for the final infiltration stage. So based on the measurements that Berta provided for the 1 cubic millimeter sample, we can take 3 grams of each of our solvent and 3 grams of our 100% resin to make a 6-gram 1-to-1 solvent ratio. And then that's still going to leave you with 8.5 grams of your 100% resin, so you can do your full infiltration. Once you have this in your conical, you can mix that thoroughly until, again, you see all the wave patterns disappear and you know you have a homogeneous mixture. So now we actually get to the infiltration itself. So our sample that has been fixed previously is in 100% solvent at this stage. So now we'll go ahead and put it in that 1-to-1 solvent resin mixture that we just made. And we'll let this sit for at least 30 minutes. I like to put it on a rotator to help infiltrate into the tissue. And then you can move on to replacing the 1-to-1 solvent resin with 100% resin. You'll do the same and let this infiltrate gently for at least 30 minutes, also at room temperature. A trick to this stage is you can leave it uncovered if you're not having it on a rotator, and the remaining solvent can evaporate. Another option for this is to just do a second 100% resin infiltration, and that'll dilute any remaining solvent. Your final stage will be to use a pipette to place some resin, 100% resin, into your embedding mold, and then placing your tissue into the embedding mold along the tapered edge. If you have an orientation that you desire to cut into your sample at, you'll want to make sure that you're considering your orientation at this stage as well. You'll be cutting along this top tapered edge here. And then your next stage is just baking at 60°C overnight, and that will polymerize the resin. If you want to avoid any hazardous waste, you can take all of your materials that had contact with your resin, and if they are all mixed together with 100% resin, you can bake everything that has 100% resin and then just throw it out as regular trash to avoid hazardous waste. And then after 1 day, you come back the next day and you have your polymerized sample. If you have any trouble removing these from the molds, you can add a Teflon spray. However, we typically don't have much issue with these brand of molds. And this, you'll see here, my sample did migrate. This was a false sample. It wasn't real tissue. So therefore, there was some air bubbles trapped in here, and so it migrated. You would not see this with your sample. It'll do a good job of staying where you put it typically. And is there any questions?
So we do have a question that was sent by email, and we're going to ask the questions at the end of both presentations. So if there's any more questions. Hemos recibido una pregunta por email que vamos a formularla al final de la presentación para que si a alguno de los participantes le surge cualquier duda a lo largo de las presentaciones lo podamos hacer al final. Podéis escribirlo en el chat o podéis escribirlo también por email. Gracias.
Okay, are you able to hear me? Okay,
Yes.
I can take over from here. Let me get my pointer. Okay, so now we're going to transition a little bit. And if you have a lot of samples or case files backing up, and you need to be able to process through your samples a little more quickly, we do have a way to do that. So that's using the Pelco BioWave Pro Plus. So this is a laboratory microwave system that allows us to drastically speed up sample processing times. So we're going to go through how to do that for EM sample prep. So starting out with just some background on microwave energy, the microwave wavelength at 2.45 gigahertz is 12.2 centimeters in air. So what that means is that within a closed microwave cavity, you get this constant standing wave pattern of that length. So what this results in is these regions of high and low energy density, which translates to hot and cold spots in the microwave. So normally in a household microwave that you might have at home, they use these hot spots and a rotating carousel to pass the food through those hot spots in order to cook the food. For a laboratory environment, we're trying to avoid cooking our samples, so we have some ways to get around that. So a little more background here. So the magnetron of the microwave is what produces the microwave energy. The waveguide directs that energy into the cabinet of the microwave. And then the wave stir ensures that those microwaves are dispersed within the cavity. So microwave energy interacts with and vibrates polar molecules. Um, Too much results in hydrogen bonds breaking and the release of heat, which is what we don't want when processing samples, since we don't want to cook our specimens. But at low energy, it imparts the movement of polar molecules and lowers the activation energy required for a reaction to occur. So by using microwave energy, we can speed up reaction rates independent of temperature or heating. And this is the microwave effect that we're trying to utilize. So one moment. So microwaves interact with different materials differently. So water molecules are one of the most absorbent materials of microwave energy because they are polar molecules. And other polar molecules as well, such as solvents and resins, are absorbative to microwaves, which results in heating. Whereas other materials, non-polar materials, aren't absorbing those microwave energies. So you either reflect or they're even transparent to the microwaves in the case of lots of plastics. So there are several variables of the microwave environment, and ideally, in a lab setting, you're going to be able to control all of these. So in a normal household microwave, they have continuous fixed power. Normally it's set to a maximum setting. They have that uneven energy field full of hot and cold spots, and there's no temperature control because the goal is to quickly heat and cook your food. Whereas in our system, we have full control over all these variables, having variable power, an even energy field, active temperature control to have no heating of your sample. So we'll start out discussing those last three variables, being the energy field and the heating rate and the heating. So in order to control those variables, we have the cold spot within our microwave system. So this is a technology which removes the standing wave pattern inside of the processing chamber, effectively acting as a heat sink. So it utilizes the polarity of water to absorb excess microwave energy in the chamber. So this is eliminating those hot spots in order to create a uniform processing environment. So that looks something like this, where on the left side, this is how a heat map of inside of a standard household microwave. So you have these hot spots in the green here, the cold spots in the blue, and it's a very uneven field. So depending on where you place your sample, you're going to have a different result. But inside of our system, we make that energy field uniform. We eliminate those hot spots, so we have full control over our microwave environment. So additionally, we have variable microwave power output with adjustable wattage. And this is also continuous controlled microwave energy as opposed to pulse power. So again, microwave energy causes a vibration of those polar molecules. At high energy, this results in the hydrogen bonds breaking, resulting in the release of heat, which we don't want. But at low energy, such as that in the BioWave, the microwave energy imparts movement to those polar molecules, producing that microwave effect without excess heat. So what this does is it limits the exposure of a specimen to the minimum energy needed for processing, and it allows microwave energy to be an active variable in the process, leading to more consistent and reproducible results. So by being designed to properly use microwave energy, the BioWave provides tools for control of the environment and the internal chamber of the microwave at the specimen level. So the most popular application for this device is for electron microscopy. This is being used in clinical and research laboratories around the world. And you can do the complete sample process from fixation all the way through to your resin polymerization. And you get results that match or even exceed the quality of conventional benchtop processing. So this is an example showing those rapid processing times that you get by utilizing the microwave effect. So on the left column, this is typical times that it takes to do these different steps for EM processing on the benchtop. This might be what you're used to doing now, something along these lines. Or on the right, this is how long it takes to do each of these steps in the BioWave. So microwave assisted tissue processing for electron microscopy is no different than conventional processing methods. The reagents that you're using in the bench are typically the same ones that you're using in the BioWave, and the number of steps are usually just converted directly into microwave steps. So you're not changing the protocol, just the timing of the protocol. Every step that you would normally do on the bench, you're doing the same thing, but you're just doing it within the microwave instead. And depending on the application, microwave processing can result in a 4, 10, or 20 times faster in your processing times. So it can be a very drastic time saving, something that would normally take a day or longer in order for you to do by traditional methods, you're able to do in a couple hours in an afternoon. So this is a sample protocol for EM, going through all these steps depending on what type of fixative you're using, all the way through to polymerizing your resin with some different options depending on what type of resin you're using, and just giving an outline of what sort of settings we're using for the microwave in order to have it set up. Also, we have some pictures here showing what the inside of the chamber looks like using some of our different processing accessories. This is a vacuum chamber, and this is a water bath that's used during the resin polymerization step. But all these protocols are empirically derived. Also, you'll notice that on the timing here, it says on, off for several of these steps. And that's because we found that continuous microwave energy over long periods of time can damage cells. So as a result, we often use this on, off cycling to avoid damaging our samples. Additionally, it's thought that allowing a return to resting state during processing is important for the completion of those reactions that are occurring. And then here's just some images showing some examples of some of these results. So on the left here, this is a canine nasal cilia using conventional benchtop processing. And then on the right, we have the same thing in the BioWave that's done in just 2 hours. So equal or oftentimes better results that we're seeing in the BioWave. And this can be done for any number of tissues from brain, heart, kidney, liver, just about anything that you can do on the bench, you can also do in the BioWave. So just to summarize here, what are advantages of using the Pelco BioWave? And that is you have rapid processing times for an overall time savings utilizing that microwave effect, but also you're able to get superior processing results because typically you'll see better structure preservation, and this is because the fixation is faster due to increased diffusion rates, but also you'll see less cellular extraction and less background staining as well. So also you have full control of your sample environment for consistent reproducible results. Also, typically the reagent volumes that you need to use are much less in the BioWave, so you save some money there too on the amount of reagent that you're having to go through. And there are oftentimes solutions that can be found for troublesome specimens. Difficult to process samples on the benchtop can sometimes come out much better in the BioWave. And it's a very versatile instrument as well. So we just talked about electron microscopy here, but people are using the BioWave for immunofluorescence, for decalcification, for histology. So one instrument can do just about any benchtop processing method much quicker. And yeah, so that's our company. And if you have any questions, I guess we can field those now.
Por favor, si alguien tiene alguna pregunta, alguna duda, podéis escribirlo por el chat. Mientras tanto, yo voy a consultar lo que nos han enviado por email. La persona nos pregunta cuál es el tiempo de curado completo de una muestra haciéndolo de forma tradicional. So we have a question for Courtney. They sent an email. So there are this person is doing the traditional bench method, and they're asking how long does it take to 100% polymerized with the Spurr resin? How many hours?
On the oven, the polymerization stage, so we typically just leave it overnight. We say overnight, usually it's done by the next day, but typically you'll see 24 hours in protocols, but it definitely is usually less. And you can always test this out to make sure, because different samples, sometimes the center might stay gummy, so you can test it out and you might be able to shave off 24 hours with different samples, particularly smaller ones usually.
Ok. Nos explican que normalmente lo dejan de un día para otro o lo que ellos consideran durante toda la noche, pero en los protocolos son 24 horas. In case they're using an oven or the microwave, could be way less. En el caso de que se utilice un horno o una fuente de calor, sería muchísimo menos. So, for example, 60 degrees, for example?
Yes, that's what we polymerize at.
Okay. Tenemos una pregunta en el chat sobre si vamos a enviar el webinar, si lo vamos a enviar. So they ask if we're going to send the video of this webinar. Yes. Sí, lo vamos a enviar. En las próximas horas tendréis el vídeo en nuestra página web y lo enviaremos por email. También las presentaciones. ¿Alguna otra pregunta? Vale. Muy bien. Nos están escribiendo, un momento. Vale. Si no hay más dudas, Paso a agradecer la colaboración de Ted Pella en este webinar. Esperamos futuras colaboraciones. Thank you very much for your help. We're looking forward for the next webinars. Y gracias a todos por asistir. Muy buenas tardes. Gracias. Hasta luego.
Thank you.
Buenas
Bye.
noches.
Thank you. Bye. Thank you. Bye.